Hello students, this is Professor Chalai, and in this video we're going to look at gas density and molar mass. As always, you can follow along with our Chapter 8 workbook. By the end of this video, you should be able to use the ideal gas law, which we used in our previous episode, or we learned in our previous episode, to calculate the densities of gases and also the molar masses of gases. Let's look at them one at a time. And let's look at density first, that we will symbolize as little d, lowercase d. We know that density is mass over volume, so m and big V, right? For molar mass, we know that, because these are the two things we're looking at, right? Density and molar mass. For molar mass, we know that molar mass is grams per mole, or mass over number of moles, MOL. Now, in this PV is equal to nRT equation, which is our ideal gas law equation, n here is a symbol for number of mole, right? So instead of, we'll just keep little n there. Okay, so now we have an expression for density and molar mass, but these are just the expression that we already know. They're not part of the ideal gas law. So let's make them part of the ideal gas law. And to do that, we'll have to do a few little tricks. First, we see that there's mass here and mass over here. So let's rewrite this equation and solve for mass. So to solve for mass, we multiply it by the number of moles on both sides, right? So we get mass is equal to the molar mass times the number of mole. So this expression of mass now, let's put it up here. So that will give us the density is equal to, instead of mass, we get the molar mass times the number of moles divided by the volume. Now look at something. N over V. We have N over V here, both of which are in the ideal gas law equation. So let's rewrite the ideal gas law equation to get what N over V is equal to. So PV is equal to nRT. We want N over V, so let's put V on this side. Let's take RT on the other side. And so this gives us N over V is equal to P over R times T. So let's, instead of N over V over here, let's substitute P over RT for that. So we get density is equal to molar mass, that hasn't changed, times, instead of N over V, I'm going to write P over R times T. And so this is the equation, how we can relate the density of a gas to the molar mass of a gas if we know the things like what pressure it's at and what temperature it's at. So all of that is summarized in these equations here. We have density, which is mass over volume, or number of moles times molar mass over volume, or the pressure times the molar mass divided by the ideal gas constant R times the temperature T. Remember, because this is an ideal gas law equation, the temperature T must always be in Kelvin. So because we're using the ideal gas law too, the volume must always be in liters, the temperature here should always be in Kelvin, and the pressure must always be in atmospheres. Yep, I think that's all that we're looking for. Okay, so now that we have a way to talk about the density of a gas and the molar mass of a gas, all from the ideal gas law equation, the rest of it is just, in problem solving, is just trying to apply this equation to various sort of situations. And so let's look at an example of that. Let's look at number 18. Here it's asking us to calculate the density of nitrogen gas at 125 degrees Celsius and pressure of 755 millimeters of mercury. So first, we're dealing with nitrogen gas. Nitrogen gas is N2, which means that the molar mass, right, is 2 times the atomic mass of nitrogen, which should come out, atomic mass of nitrogen is 14.01 grams per mole times 2. So this gives us 28.02 grams per mole. The other thing this equation gives us is the temperature, right, 125 degrees Celsius, but again, ideal gas law type problem, so we need to convert this to kelvins, and so that should give us 398 kelvins, and they give us the pressure of 755 millimeters of mercury, but again, ideal gas law, so we need to convert this to atmospheres. We know that 760 millimeters of mercury is 1 atmosphere, and so if we convert it to atmospheres, we get 0.993 atmospheres. So that's all they give us. It's nitrogen gas, so we know the formula and therefore the molar mass, the temperature, and the pressure. So now we just need to use this equation to figure out density. We know the molar mass. We don't know number of moles, so we can't use this part of the equation. But we do know these components. We know the pressure. We know the molar mass. We always know R, and we know the temperature in Kelvin. So we can just set that up. So let me set that up. The density is up here. The pressure times the molar mass divided by R times T. So the pressure times the molar mass divided by R times T. The pressure is right there, 0.993 atmospheres. The molar mass is 28.02 grams per mole. R is the ideal gas constant, it's 0.08206 liters times atmospheres divided by moles times Kelvin. And the temperature is 398 Kelvin. All right, let's just see what all the things that cancel. Atmospheres cancel with atmospheres, moles with moles, Kelvin with Kelvin, and we're left with grams over liters. So that's what our density is going to be in, grams over liters. And if I punch this into my calculator, I should get 0.852 grams over liters. If you want to convert this to grams over milliliters, right, you just divide by 1,000. But in this case, they didn't say what units to put the density in, so we'll keep it as grams over liters, mass over volume. Okay, with that, you now have sort of the equations and the tools to go about and answer all of the other questions. So if you'd like, you can pause the video here and go do that now. And then when you unpause, I'll go over each one of them and show you how they're done. Okay, let's look at number 19. So number 19, they tell us that it's xenon gas, right? So that means that the molar mass of xenon, you just need to look at a periodic table. Xenon is a noble gas, which means it should just exist as one atom, xenon. It doesn't bind to anything because it's a noble gas. So the atomic mass of xenon, which is the molar mass of xenon gas, is 131.29 grams per mole. Okay, the pressure is 742 millimeters of mercury, but again, we need to divide by 760 because we need to convert it to atmospheres. And so that comes out to 0.976 atmospheres. And finally, they give us the temperature, but only in degrees Celsius. So we need to add 273.15 to convert it to Kelvin, and that comes out to be 318 Kelvin. Now that we have that, again, we can find the density as we use the same equation up here. The pressure times the molar mass divided by the ideal gas constant R times the temperature T. So we got 0.976 atmospheres times the molar mass of 131.29 grams per mole divided by R, 0.08206 liters times atmospheres divided by moles times Kelvin times the temperature, which is 318 Kelvin. Okay, so what? Kelvin cancels, moles cancel, atmospheres cancel, we're left with grams over liters again. I mean, it's the same equation, so we're left with the same units. Plug all of this into a calculator and I get 4.91 grams per liter. So here's a situation where we have two different gases in these two questions with different molar masses, similar, right, similar pressure, and I mean, not two different temperatures, and we see that one has a much higher molar mass compared to the earlier one, and also much higher density than the earlier one. If we look at this equation right here, the density is equal to pressure times molar mass divided by R times T. If the pressure and the temperature are the same, right, then the density is related to the molar mass. The higher molar mass you have, the denser your gas. The lower molar mass, the lower your density of gas. So think about that for the future, right? Think about what the molar mass of a gas is, and that's how you can figure out the density of a gas. Now, when you do that, think about the components of air. It has nitrogen gas, oxygen gas, carbon dioxide, and some other things. Think about which one of those are more dense than the other, and yeah, and sort of what their densities are compared to each other. All right, if you haven't tried number 20 yet, please try it on your own first. It's a little bit different, and let's see what you get. Okay, so number 20 says the density of a gas is 1.43 grams per liter. So density is 1.43 grams over liters. I like to write all of the pieces of information the question gives me, even though it's right there in the question. The temperature is 23 degrees Celsius, but we need that in Kelvin. So that gives me 296 Kelvin. And the pressure is 0.789 atmospheres. It's already in atmospheres. I don't need to convert. In this question, they're asking us to calculate the molar mass of this gas, right? So here they give us the density, a temperature and pressure, and they want to calculate the molar mass. So I'm going to take this equation and just resolve it for the molar mass instead of the density. So density is equal to pressure times molar mass divided by R times T. I'm solving for molar mass, so I just put things on the other side, right? So the molar mass then should be the density times R times T, right? That I multiplied by R times T on both sides, divided by pressure, because I divide by pressure on both sides. A good way to make sure that your formula works is to write all the units and make sure they cancel out to give you the correct units. So let's do that. So the molar mass is the density, which is 1.43 grams over liters, times R, 0.08206, liters times atmospheres divided by moles times Kelvin, times the temperature in kelvins, that's 296 kelvins, all divided by the pressure, which is 0.789 atmospheres. Okay, let's see what cancels out. We have liters with liters, atmospheres with atmospheres, Kelvin with Kelvin. And so the units we're left with is grams divided by moles. Well, that is the unit for molar mass, grams over moles, right? Gram per mole. So that makes sense. Our formula made sense. We're looking for molar mass. Our units that we're left with is grams per mole. So I run all of this in my calculator and I get 44.02 grams per mole. Or really 44.0 to 3 sig figs. Now, we've been working with a few gases so far in the semester. Which gas that we've worked with has a molar mass of 44.0 grams per mole? If you're thinking carbon dioxide, you're right. So this gas, we don't know for sure, but based off the molar mass, it's probably carbon dioxide. All right, let's look at number 21. Arrange the following gases in an order of increasing density at standard temperature and pressure. Remember, standard temperature and pressure just means for pressure, it's 1 atmosphere. For temperature, it's 0 degrees Celsius or 273 degrees Kelvin. Excuse me. So, arrange them in order of increasing density. Earlier, we said that density is related to the molar mass. If temperature and pressure are the same, in which case it's all the same because it's at standard temperature and pressure. So in order to figure out what their densities are, we just need to figure out what their molar masses are. And so let's see. Neon has a molar mass of 20.18 grams per mole. Right? We know this. We just look at the periodic table. Cl2 has a molar mass of 70.90 grams per mole. Fluorine has a molar mass of 38.00 grams per mole, right? You just take the molar mass of fluorine, which is 19, multiplied by 2. And oxygen would just be 32 grams per mole because we just take the molar mass of oxygen, 16.00, multiply that by 2. So, in order of increasing density, it's the same as the order of increasing molar mass. The lowest we have is neon, followed by, what's next? Oxygen, followed by fluorine, followed by chlorine. So there we have it. These gases listed in increasing densities. All right, if you haven't tried number 22 yet, please do so first, and then we'll go over it together. So here we have a sample of gas. They give us the mass. So let me just write that. Mass is 0.311 grams. They give us a volume, right? 0.225 liters. They give us a temperature, 55 degrees Celsius, but again, we need this in Kelvin, so that comes out to 328 Kelvin. And finally, they give us a pressure of 886 millimeters of mercury. But we know that we got to divide that by 760 to convert it to atmospheres, which gives me 1.17 atmospheres to 3 sig figs. Okay, now we need to find the molar mass. Now let's go back up to this equation that we just worked with. The molar mass was the density times R times T divided by P. Right? So the molar mass is the density times R times T divided by P. Now we don't have the density, but we have mass over volume. So instead of density, I'll put mass over volume. Let's see if this works out. The molar mass is, let's put the mass in there, 0.311 grams. R is 0.08206 liters times atmospheres divided by moles times Kelvin. And temperature in this case was 328 kelvins. I divide that by the volume, which is 0.225 liters. And then I divide that by the pressure, which was 1.17 atmospheres. All right, here's the fun part. Cancellation of units. We got grams with nothing. Okay, we got atmospheres with atmospheres, liters with liters, Kelvin with Kelvin, and we're left with grams over moles, which is exactly what we wanted. Grams over moles because it's the molar mass. I plug all of this into my calculator and I get, I believe, 31.8 grams per mole to 3 sig figs. Now you might be wondering what gas is that? 38.1 grams per mole. According to this little molar masses of these gases that we did earlier, 32 grams per mole is oxygen, which is close enough to 31.8 grams per mole. So maybe this is oxygen. And it's just a little bit of rounding error that 31.8 to 32 is not that big a deal. All right, let's try another one. Number 23. If again you haven't done it yet, please pause the video and do so first. So it's a similar question. They give us a mass, but in milligrams. We know that for molar masses, we need masses in grams, right? So 827 milligrams. So that means we just convert this to grams. 1,000 milligrams is a gram, so this would give us 0.827 grams. All right, they give us the volume, so there we go, 0.270 liters. They give us the temperature, 88 degrees Celsius, but if I convert that to Kelvin, I get 361 Kelvin. And finally, the pressure, we get 975 millimeters of mercury, but we want to convert that to atmospheres. And so that gives me, let me see, 1.28 atmospheres. So you see, this is the first step in a lot of these gas problems, is to convert to the units that you need to work in, right? Masses typically in grams. Volume for gases will need to be in liters. Temperature for gases need to be in Kelvin. Pressures need to be in atmospheres. Why? Because our ideal gas constant, R, is in units of liters times atmospheres divided by moles times Kelvin. So those are the units we need to use. All right. So we're looking for the molar mass again, and that means we can just use this equation up here, right? So the molar mass, that's not an M, but it's close enough. Molar mass is the mass times the ideal gas constant times temperature divided by volume times pressure. So let's put all of those in, right? The mass is 0.827 grams. R is, as always, this long number, which you don't need to memorize, but I've just accidentally memorized it because I use it so often. But you need to recognize it quickly to use it in problem solving. What's the temperature? 361. Divided by the volume, 0.270 liters, and the pressure is 1.28 atmospheres. Now we did this above, so we know the units should cancel out, but you know what? I like canceling units, so let's do that. And we get grams over moles. That's the molar mass, so that's okay. Grams over moles. I plug this in a calculator and I get 70.9 grams per mole. 70.9. So if we're wondering what gas that might be, I mean, you probably don't know all of the gases in the world, but we did look at Cl2 here and we saw that it was 70.9, so it's probably Cl2, right? Could be other gases, probably not, because I probably use Cl2 to write this question. So there we have it. We have a way to relate the density of a gas to its molar mass by recognizing that we can rewrite it in terms of the ideal gas equation that we derived over here. So we got density, we got molar mass, we try to put them together using the ideal gas-like equation, and we got this guy right here. So once you know the pressure and the temperature and the density, you can find the molar mass. Once you know the molar mass, the pressure, and the temperature, you can find the density. They're all in this equation. All right, in our next video, we're going to look at pressure of mixtures of gases. So far, we've been looking at only one kind of gas at a time. In our next video, we're going to look at when we have two different gases together. I'll see you then.